Tamara. Sarah Hitchner. Alice. Erica. Sorry. Nora, I think Nora is you. Percy. Sinead. Alda. Lauren. Shonda.
So we were like seven shirts and she comes out her
Yeah, I posted it.
You made that stupid say.
Yes, Nia. Yunwan Zhang. Yunwan. Surecha. Rachel Cogney. Tiffany. Ashley. Kyla. Diane. Marina. Erika. Caitlin. Angela. Taylor Sanchez. Neha. Anna. Zoe. Rachel. Taylor. Elena. Okay, so Taylor, yeah, this is the,
So then we're just like walking.
Kyla. This is the quiz that was missing. Chonda. Yunwan.
You just see my hand going like this and keep throwing them in a ring. I'm scratching in the other. We have a standing ovation.
This is the science of thermodynamics in action. The science of heat transformed into mechanical energy. The power-driven machinery of the Industrial Revolution depended on it.
Heat energy can be turned into into the energy of motion, such as by turning a crank or a piston or a turbine to be used to pump water, to turn the loom to make fabric, to move a boat through the water, to move a train down rails. Now it's desirable to get more oomph for your dollar, to get more work done for the amount of fuel you're going to use. And so people began to study how heat engines, how steam engines really work.
Among those who studied it was a German scientist named Rudolf Clausius, who in 1865 formulated our next great discovery, what became known as the second law of thermodynamics. The law states that in any energy exchange, such as heating the water in a steam engine boiler, some energy is always wasted. Clausius coined the word entropy to explain why the efficiency of a steam engine is limited. Because some of its energy will always be lost in the process of converting it to mechanical work. It was a momentous insight, one that changed our understanding of how energy works.
There's no heat engine that is 100% efficient. When a car is moving along, how much of the energy implicit in the gasoline that you put into a car actually gets used to move the car and you in it? Only about 20%. Where does the rest of it go? It goes to heating up the pavement on the road, heating up the tires. The cylinders in the engine block get hotter. They wear out. Parts corrode. It's sobering to think how wasteful these processes are.
While the second law of thermodynamics was a driving force behind the Industrial Revolution, our next great discovery.
All right, so what we're going to talk about is the second law of thermodynamics. It has profound consequences to our everyday life. You can essentially blame the energy crisis on the second law of thermodynamics. If not for the second law of thermodynamics, humanity would not be facing such a huge challenge ahead of us. We wouldn't have to even worry about global warming. Blame it on the second law of thermodynamics. Okay? Very profound. Our applications are going to be slightly different. We're going to use the second law of thermodynamics to tell us if a chemical reaction is spontaneous or not. That's the goal of the next few lectures. How can we use the second law of thermodynamics to tell us if a chemical reaction is spontaneous or not? All right? So I want to apologize in advance. I somehow or other damaged my glasses this morning, and so I'm wearing a pair of glasses that are about 4 years old, and my prescription is a little bit different, and I have a splitting headache right now. So I apologize if I don't make myself very clear today. All right, so you get to see one of my other favorite movies. Perfect before. This is the second law in action. What happened to the clock? Do you notice? Okay, let me play that over again. talk about that later. Okay? But this is essentially what the second law is all about. The first process is a spontaneous process. The second process is a non-spontaneous process. And I will define what spontaneity is. A spontaneous process occurs without outside intervention. You don't have to do anything. It'll happen by itself. That's what a spontaneous process is. A non-spontaneous process requires you to do something to the system to make that process happen. So here is a set of two flasks connected by a stopcock. All the gas molecules are on the left-hand side. There are no gas molecules on the right-hand side. You open the stopcock, and the gas molecules evenly distribute themselves between the two. Going from here to here is a spontaneous process. Going from here to here is a non-spontaneous process. Yes, Tamara?
No, I was just thinking, I was looking.
Can you repeat that again, please?
Yes. Going from A to B is a spontaneous process. It'll happen without any outside intervention. This, from B to A, is not going to happen spontaneously. Think about it. You're in this room. The molecules are evenly distributed. Will all of the molecules suddenly show up on one half of the room and leave the other half totally a vacuum? The probability of that happening is very, 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 very small. You would have to live for multiple ages of the universe for that to happen. I'm getting to a concept called entropy, and entropy is related to probability. It's not that this will never go to this, but that this going to this is very, 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 very unlikely. You can calculate the probabilities. When it becomes an Avogadro number of molecules, this going to this is essentially zero. I've got to tell you a story. When I was new here to Wellesley College about, in the early 90s, there was a memo that was sent out saying that if you want to have your flow vacuumed, there should be nothing on the floor. Okay? So I decided to do a calculation. What is the probability of spontaneously levitating a desk? Okay? And how many years would it take for a custodian to peek inside the room and find the desk levitated with a probability of 90%? Okay? This is a very, very interesting calculation, and I will spend an entire lecture in the first semester physical chemistry course talking about this calculation. The number of years is 10 to the power 23 years. Okay? For a custodian to open a door and find a table levitated with a probability of 90%. You know the age of the universe, right? What's it? 10 to the power? Rachel?
I was going to say 14 billion years.
14 billion years. That is correct. And so it's about 10 to the power 9 years, or 10 to the power 10 years. Yeah. Okay? You cannot imagine the difference between these two number of years. There's no way you can even imagine it. Okay? but I'll leave that for PChem 1. Okay, let's look at another movie.
Molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have reached thermal equilibrium and have the same temperature.
So, heat always moves from a hotter object to a colder object. Remember that song that I played for you? Okay? That's the second law of thermodynamics. Okay?
Professor,
Yes.
in the video we just saw, is that an example of non-spontaneous because we're adding something?
No, not really. The second law of thermodynamics can be stated in a different way. And in terms of heat engines, you can say that you can never make a heat engine that is 100% efficient. Okay? There's a little bit of material in the footnotes in one of my in today's lecture, beyond the scope of what I want to do in this course. Okay, but so it's not a non-spontaneous process. Okay. All right. Quite often we think that if you start off with a system at a high energy and you want to go to a system with a lower energy, then that process is going to be spontaneous. That's a misconception. Seeking the state of minimum energy is insufficient to explain many chemical and physical changes. If you take a piece of ice and leave it on this table, what will happen to that ice? It will melt. Is that an exothermic process or is it an endothermic process? It is an endothermic process. Energy is being absorbed. Yet, it is a spontaneous process. So, minimizing energy cannot be the sole criterion for determining a spontaneous process. Very, very important observation. Here is another example. What am I looking for? Oh, everything is blurry.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
Okay, endothermic reactions can be spontaneous. Okay, so what we're going to say is that spontaneity is determined by molecular chaos, and if you increase molecular chaos, then that process is going to be a spontaneous process. You might have heard people say that spontaneous reactions are favored when disorder increases. Most of the time that statement is true. But a more precise way of stating the second law of thermodynamics is to say that spontaneous processes are accompanied by degradation of energy. And we're going to talk about a state function that is going to be a measure of the spontaneity of a process. And that state function is what we're going to call entropy. So entropy in every introductory chemistry textbook is a measure of the randomness or the disorder of a system. Okay? The more the disorder, the higher the entropy. That's what every chemistry textbook tells you. But a more precise statement is that entropy is a measure of the dispersal of energy. How is energy dispersed in the system? The more the dispersal, the higher the entropy. I'm not going to make a big deal about the correct definition of entropy. But my notes are very precise in defining entropy. So during class, I'm going to talk more in terms of disorder, which is what every introductory chemistry textbook says. Why? It's very easy to understand. Okay? But when you read the notes, you will see that disorder does not always correspond to the concept of entropy. So here is a demonstration. Let's look at states.
Molecular motions are much more random in the gas state than in either the liquid or solid states. Motion in a liquid is more random than that of a solid. Gases tend to have the highest entropies, while solids have the lowest.
So there is more disorder here compared to liquids. Liquids have more disorder compared to solids. So the entropy of the gas is higher than the entropy of the liquid, which is higher than the entropy of the solid. Okay? Not quite correct, but we'll leave it at that. During lecture, I'll ask you to read it more carefully in the notes. What we're going to see very shortly is that entropy is a direct measure of the number of microstates accessible to a system. So what is a microstate? And I'm going to use a definition given by Richard Feynman. Does anyone know who Richard Feynman was? Angela? He was a physicist. Rachel?
Yeah, he's one of the most famous physicists of the 20th century.
I would say the second most physicist after Albert Einstein. Okay? He has written many popular books. Surely you must be joking, Mr. Feynman. An incredibly brilliant guy. He was one of the people who said, I don't understand quantum mechanics, nobody does. Feynman said, a microstate corresponds to changing the inside without changing the outside. Changing the inside without changing the outside. What does he mean by that? Okay, I'm going to demonstrate that to you with another movie with some nice music too. So we're going to look at two flasks connected by a stopcock, with the left flask containing 4 labeled balls and the right flask empty. And we're going to look at how these label bonds are going to distribute themselves between the two flowers. And when I show the movie, I want you to pay attention to what's shown on the top left-hand corner. Each of those images corresponds to one of these images here. All right? Three balls left, one ball on the right. Now 2 and 2. These are all the different microstates for 2 and 2. So how many microstates were there for 2 and 2? 6. 2 and 2 is a macrostate. Corresponding to that macrostate, there are 6 microstates. Okay, so let's look at 4 on the left and 0 on the right. How many microstates? 1, 3 on the left and 1 on the right. 4, 6, 4 and 1. So this state here, 2 on the left and 2 on the right, has the most number of microstates. And it's most likely that the system is going to evolve to this state rather than to any of the other macrostates.
Professor A, can you explain why again?
So because there are more microstates associated with this macrostate than any of the other macrostates. So if you randomly allow the system to evolve, this macrostate is going to result more often than any of the other 4 macrostates. Okay? So then the question is, which of the macrostates has the highest entropy? And we're going to answer that question using what's called the Boltzmann formula. And here is the Boltzmann formula. On the left-hand side is the entropy. The symbol is S. K sub B is the Boltzmann constant. It's a universal constant. And Ln is the natural log. And W is the number of microstates corresponding to a macrostate. the Boltzmann constant is equal to the gas constant divided by Avogadro's number. All right, before I say anything further, I want you to look at this image here. What do you think this is an image of? Sorry, Rachel?
It's a bust of Ludwig Boltzmann.
Okay, very true. There's something a little bit more interesting than what you said. Sorry?
Tombstone?
His tombstone. If you go to Austria, in Vienna, there's tombstone that you can go visit. And look what's written on the top. Okay? At that time, they didn't have the symbol Ln. Okay? A very, very important equation. So again, W is the number of microstates. This is what Feynman said. W is the number of ways of changing the inside without changing the outside. This is probably the most profound yet simple definition of W that you can think of. All right, let's make sure that we understand this concept. If a system has only one way of achieving the given energy, what is the entropy of the system? Can you take a minute to think about it and then talk to your neighbor and convince your neighbor that you're right and your neighbor is wrong? And the answer in one voice? Zero. Zero. Very good. Okay. This leads us to the third law of thermodynamics, which says that the entropy of a pure, perfect crystalline substance is zero at 0 Kelvin. Yes?
Sorry, just to clarify on that one. So when you say that there's only one way of achieving given energy, you're saying there's a microstate of 1.
Right.
Okay.
Okay, W is equal to 1. Therefore, entropy is equal to 0.
Thank you.
So think about this. If you cool a substance that is a pure, perfect crystalline substance to 0 Kelvin, there's only one way that that substance can arrange the atoms and molecules consisting of it. So W for that substance at 0 Kelvin is going to be 1, and therefore the entropy of a pure, perfect crystalline solid is going to be 0. This is the third law of thermodynamics. This has profound consequences, one of which is to say that you cannot ever reach 0 Kelvin. This is an absolute law. Come 1,000 years, come 2,000 years, no technology will ever be able to reach 0 Kelvin. That's one way of stating the third law of thermodynamics. Right now, I think the record is about 10 to the power minus 9 Kelvin. Okay, maybe we can go to 10 to the power